So first of all, give me a feedback whether the pace at which we are going and the concept that we are talking, I'm taking a lot of diversions. I'm digressing a lot. Is that something that you like or you don't like, or you want me to just stick to my slides and then do? Is this better? Good. So that it's good to as critical minerals. By the end of this 2 weeks, you should appreciate critical minerals are but there's more to critical minerals than just technology. There's so many solutions: how to crush, how to grind, how to separate, what chemicals to use. In fact, to be very precise, if you look at rare earth extraction, rare earth elements, there are about 1,000 different chemistries. 1,000. Extraction and processing. Separation. One of our colleagues who is speaking on Dr. Sai Pranit, right?
Yes, sir, Sai Pranit.
And Dr. Sai Pranit is going to talk about separation. Yeah, separation. Yeah, material. So if you look at this, you are separate, or you can extract, processing different chemicals. And if someone comes with HNO3 and so forth, simple. What are the typical metallurgical processes? Hydro, yeah, and then pyro. Does anyone, those are non-engineering background, do they know, like you are non-engineering, right? Do you know what is pyro? No. Who else is non-engineering here in the room? From geology, geophysics. You know pyro and hydro. Have you heard of them? You heard, yeah. So hydro is what? Water. Hydro is water, right? So that's something liquid, yeah? Right? Solvents. Solvents. Pyro is what? Heat, high temperature. With we becoming environmentally conscious, and decarbonization is one of the prime movers of the entire critical mineral space, and then net zero. What is net zero, by the way? Right. So offsetting and emission, right? That's net zero. And India has pledged to achieve net zero. That means whatever CO2 emissions or greenhouse gas emissions. What are the greenhouse gases? Methane, yeah. CH4. CO2. CFCs. Water vapor, yes. Yeah. So these are greenhouse gases. And some have high greenhouse gas potential, like, climate change potential, global warming. We call it global warming potential. Global warming potential. Some have it less. For example, methane has the highest global warming potential. Carbon dioxide is moderate, and water vapor and others are minor. So these are global warming potential is, if these continue to emit in whatever concentration that they emit, how much effect, re-radiation effect that they will have on the globe. That is what is global warming potential. So net zero is what India has pledged that they would achieve by 2070. That means whatever net emissions are equal to net savings. That's where net zero. Now, if you look at just your IIT campus itself, there are so many activities that are ongoing. You use a lot of electricity, you use water, you use a number of other things. But if you've got enough plantation, then it will see the emissions that you produce or at least part of that is, so you have solar energy through solar wind, then that would also offset. So like if you do entire life cycle emission accounting, then that would give you net zero, right? So pyro being high energy, do you know what is the steel and any metallurgist? Was your PhD in that area, pyro? But what is the temperatures that generally we are looking at in aluminum smelting and steel? About 1500 degrees. Just imagine 1500 degrees of temperature and Tata Steel, right? 1500 is a reasonable assumption. Yeah. Then the related CO2 emissions, both through your coking coal and also the energy that you derive, because most of our energy is also fossil fuel energy. That means you'll have cumulative effect of that, right? So hence, generally people are saying no to pyro. You cannot say completely no, but trying to be as minimal as yes to more of hydro. So hydrometallurgy, solvent extraction, and electrowinning. That's a typical electrowinning, right? You have cathodes. What they do is, now you got rock, you crush it into very fine talcum powder kind of consistency. And then what we said is, you get only 2% copper. So if you take 1 kilogram of rock, you crush it into powder, talcum powder, you have got only 2% of it as copper. How many grams it is? 20 grams, is it? 2%. Yeah, that's right. 20 grams. 20 grams of copper in among rest 980 grams of dirt. How do you liberate? How do you separate? And in one of the lectures in the next couple of days, we will come back to what are the key transitions that mineral industry has seen in the past 2 decades. One of the key transition is the mineralogy has changed drastically. There was a time when we had coarse grain mineralogy, right? To separate coarse grain, the grinding don't have to be as finer as it is to separate finer material, right? If you've got gold nugget, you can easily pick and choose, no? Like you can take out, okay, this is gold nugget, it's gone. If you're in quads in a very tiny bits and pieces, then you'll have to do a lot of crushing and grinding, where you expend a lot more energy, right? That's one of the key industry transition that mining industry has seen. So in order to separate, what you have to do is you have to do fine grinding. And then you have to separate that 20 grams contained in 1000 grams, for which we use different solvents. Traditional solvents had been high intensity chemicals or acids, right? What are they? Sulfuric acid and H2SO4, HCl, HNO3, right? These are the powerful. So for our friend here who is non-engineering, they are like, if you touch them, they'll burn your skin. Acids, right? What you do now? That's your beaker. Again, my chemical engineer friends in the room will smile. That's your beaker. So this is your crushed powder. and then you put liquid into it. Simple, to simply put. This is what these chemical engineers do in the room. What they do, they put this and then they mix it so that the precipitate, and then all the supernatant will be drained so that you have got concentrate. Yesterday, you remember we talked about the concentrate. So if you got 2%, we will concentrate it to 30%, and then 99.99%. That's your final refined copper.
That's at pH and temperature.
Right?
Temperature.
Yeah. So the detailed nuts and bolts are, you control temperature, you do it, this speed, it, and then you add this chemical, that chemical, and then. So what we are saying is there are about 1,000 different processes established worldwide, and then still people are trying to look at. For example, in my own we have 3 projects that are currently in progress. They are using deep eutectic solvents. I don't even know how to pronounce it also. Is it? Have you worked in that area? Okay. Friendly. Yeah. So deep eutectic solvents is what, these are very harmful. Even the disposal will be a lot of headache, right? But at least they are not as intense as this, right? So they are organic. Yeah, I'm not no expert in that, but my colleagues who are experts in that, they keep saying, they are better, they are better. And again, there's a lot of uptake of that kind of research. At Monash, at least we have 3 PhDs who are working in this area, where they have separated, the black mass, your recycling thing. Now we have reached to TRL4. TRL4. We are looking for commercial partners. Again, many labs are doing this. So there's a lot of companies which have commercially deployable technologies developed through use of deep eutectic solvents. So this is hydro, which is benign compared to this. Even if you dispose, for example, that is localized compared to the pyro. Pyro is more global, right? Because you heat it up, those gases and whatnot, it has its own problems. All right. So this is exactly what they do. These mineral processing engineers in the room.
Consider carbon and cobalt. Initially, it is coming from concentrate, then start to bleaching to electrowinning. The end of the process, it may take, in general, the moderate industries, 15 to 30 cycle. And you can imagine what will be the working process. So the decanters and the reaction methods, teaching tanks. So almost 10 days of production will be there in the WIP. Completely, it's quite a different game. But I can say people has to work with. In 2005, I think in 2007 or 8, this copper price is almost $5,000. Suddenly, it was down to $200.
Exactly.
So at that time, production cost is $2,800. Then cobalt, luckily, copper and cobalt both are together with the oxide forms. Cobalt is at that time is 10 to 12,000 US dollars. Then it was enhanced to $60,000. So the copper price fall down is compensated with the cobalt price enhancement.
Daily like some company have this crushing machines and all, but they don't have they you mentioned about the powder. They don't have any technology for these so can you transfer to other companies or if process the security remain same or is it or is anything happen in that process? I want to know. And probably actually for carbon because now
No.
for prices falling down probably because now government has to having carbon credit as well.
I'm talking about in 2005 to 2008 time, because always there will be every 10 years this kind of course now it was enhanced with the geopolitical. Uh,
Yeah.
Business or that already has that technology to provide for that company.
Very good. Excellent question. Again, that when we talk about economics tomorrow, we'll touch upon some of that points. We'll come back to that. It's a very, very, very important point because yesterday I was telling the friend who has got business and they collect tax royalties. So generally, tax is a term that we are very familiar. Royalty is a mining specific term. Royalty is a mining tax rather, right? So for every ton of ore that you extract, you will have to pay royalty to. See, the word of royalty came from because royals, right? The British royals, and that's how it came. Then you have to pay that to government, and then what was the name? Bharat. Bharat's business is about collection of that for on behalf of the government for, for Andhra Pradesh state. I think a couple of districts that they control. No, that's a very important point. We'll touch upon that. But anyway, yeah, JVs. Yeah, yeah, that's a good point that you made. There's something called KABIL, KABIL, Khanij Videsh India Limited, right? So this is a joint venture between HCL, Hindustan Copper Limited. No, no, no. Nalco, yeah, Nalco, National Aluminium Nalco. MECL, Mineral Exploration Corporation Limited. This is one fourth one. Nalco, HCL, Nalco, MECL. No, no, Coal India is not there. Only three? Are you sure? Okay, tripod. Okay, okay. I think that I was under the impression that there is a fourth one. Okay, there are only three. So these three have already formed that. And because your area is a bit of policy, so you know why it was formed. So they wanted to raise a corpus that is substantial enough where Indian government will send this Kabil, because this is mainly Indian government's external entity. Inward anyway, they're individually they are managing, but when they go outside, Kabil will represent them. Exactly. So they are now kind of taking a lot of leases in Argentina, lithium triangle country. Yeah. What is lithium triangle? ABC countries they call A, B, C. Argentina, Brazil, and Chile. Chile. Huh? So ABC, lithium triangle they call it. Lithium triangle. Sorry, my handwriting is a little bad. So that's the lithium triangle. Do you know lithium? What are the types of ores in lithium?
Spodumene.
Spodumene, excellent. So lithium is sourced in two forms. One is through spodumene, which is Australia spodumene. Yeah, but brines, the major sources, if you look at brines. So most of Latin America is brines. Brines are like they are in the liquid form, right? So spodumene is in the rocky form. Typical concentration is about 1%. So if you dug up 1 ton of rock, 1% of that would be how much? 1 kilogram, right? 1% of 1,000 kilograms is one. Only 1 kilogram will be lithium. 99,900 kilograms will be your tailings. Just imagine, as we discuss again tomorrow, we are going to talk about best practice environmental management. The problem is huge. Where do you put this? One, you are making a big hole in the ground. Millions and millions of tons you have to do extraction. Our friend mining engineer, that's what they are good at, digging stuff, right? And then second, you'll have to manage, the waste. Do we have any environmental engineers in the room? But anyway, most chemical engineers are environmental anyway, right? Yeah. Yeah. So, brines. Now, India, again, it's minerals diplomacy, geopolitics at play. In fact, I have been recommending that yesterday we talked about few alliances, right? US led, what is the association called? The one which is led by US, which has 23 member countries. Partnership, minerals security. So likewise, I have been recommending to Government of India that Government of India should take a lead in setting up a global south. Have you done some research on global south? Global south, what is under global south? No, Australia doesn't come.
So,
So, Asia, South Asia, Africa, and then South America. Yeah. Yeah, Latin America is South America, right? So mineral security partnership has 23. Now what I said is Global South Critical Minerals Alliance. Because if you look at PGMs, platinum group of minerals, which are very, very important for catalytic property, a lot of catalysts. PGM, South Africa is having highest reserves of PGMs. Ghana, 60%. Sorry, not Ghana. Yeah, of course, Indonesia, nickel, Indonesia. Do you know, second largest deposits of rare earths are in Vietnam. World's second largest deposits. Huh? The US and Vietnam went for war, and then Vietnam defeated US. And if you antagonize them further, then they will align with China. So it is in the strategy. So you play geopolitics in the way that they are sensitive to, all that. So now you understood, right? That so when next time when I say hydro, this is exactly what they do. chemical engineers, they are good at. So our friend geologist is good at finding out, and our mining engineer is finding good at digging stuff, and then our chemists are good at crushing, grinding, and then separation. And then some material scientists are good at finding out, how do we dope them together. We talked about, you remember, arsenic, cadmium, gallium, different proportions that you mix, and then you create an alloy. So that's how the whole thing works. But what is important? Okay, this is not it all of critical minerals. The critical minerals are more about it, geopolitics, more about economics, more about how do you source, how do you secure, how do you manage the supply chains, right? So is this clear to everyone now? Yeah. So what I'm saying is, uh, the inner where mining happens for these metals, right? You can see a bauxite mine for aluminum, and you can see a lead mine. You can see an iron ore mine. Who was saying Tata Steel now? So Tata Steel requires a lot of steel, like iron ore. Generally, iron ore is found in 60 to 70%. So if you dug up 1 ton of rock, 70% of it would be Fe, which is very highly concentrated form. So there's no further beneficiation. The beneficiation is only to remove some gang minerals, some penalty minerals, right? And these are the primary ore minerals. And these are associated companion minerals, we call it, or hitchhiker minerals. If you look at today, tellurium and selenium and tellurium are sourced as byproducts of copper mining, copper slimes. 100% of these two metals are being sourced as a byproduct of copper mining. Same with gallium. Gallium currently is sourced as a byproduct of aluminum or bauxite mining. Hafnium and zirconium, right? Titanium. They come as titanium. And then rhodium, iridium. What is Ru? Ruthenium, yeah. OS, osmium, right? That is sourced as platinum group of PT is platinum, right? So that means this is 100%. And then when you go a circle outwards, these are sourced 75%. 75% of them are sourced. For example, if you look at Nd, neodymium, praseodymium, cerium, lanthanum. These are light rare earth metals. So again, within the rare earth family, there are light rare earths and heavy rare earths. Cerium, I think up to cerium, lanthanum, cerium, neodymium, praseodymium. These are the 4 light rare earth metals. And then after that, terbium, dysprosium, europium, all of them will fall under heavy rare earth metals. We'll come to some of that when other professors are going to talk about them. By the way, another important thing. In fact, this is something when I took a delegation to Honorable Education Minister of India, Dharmendra Pradhan. Again, because I said that I'm the co-founder of Australia India Critical Minerals Research Hub. We wanted to take our message to the key policymakers, because policymakers are the ones who sign the checks, right? And one of the key things, if you have to progress as a country, you have to spend money on research, innovation. Where the talent is in here, in the form of you. Because you have brilliant ideas, and then you will test those hypotheses, and then you will come out with whatever outcomes that you. So, for example, now she has developed a TRL level 3 kind of outcomes of our PhD. So we said that how China of India, which has only 10,000 members. And this is a very specialist branch. Within the metallurgy, for example, if you consider, rare earth would be a very small, tiny fraction. And in China, they've got 120,000 members, means 120,000 people, which are professionals from industry, scientists from universities, research labs, and government, and so on. So they have collectively worked on one single cause, that is secure, monopolize, develop technologies for rare earths extraction, processing, separation, and magnets. So just one tiny bit of professional body has 120,000 members. Very conscious effort, right? Again, going back to what one of the Chinese presidents said is, if Middle East has oil, China has rare earths. So to match that vision, they put money behind industry, money behind R&D, money behind professional society, and hence they have that 98% control of 90-80. And in contrast, I say this, there is a society called Oz IMM. IMM. I think it's South African Institute of Mining and Metallurgy. And then US, it's called Society of Mining Engineers, SMI. So SMI, South African Institute of Mining and Metallurgy, Canadian Institute of Mining, Australasian Institute of Mining and Metallurgy. The combined membership of these organizations is less than 30,000. And Chinese Society for Rare Earths, which is this is mining as a whole, this is just rare earths, has 100,000 members. See the contrast. This is combined total membership less than 30,000. So that is the power of achieving the excellence. No one can compete, no one can even stand. So what I was saying is we need to build in India for this. And then when we went to Minister Pradhan, he gave us about 30 minutes time. Then I was telling him, Minister, because ministers may not have, they are not subject matter experts, but they grasp quickly things very quickly. Minister, there was a time we used to consider chromium, cadmium, right? Because when I saw that cadmium, I wanted to tell this story, right? Cadmium, arsenic, chromium, they were considered as environmental nuisance, right? Exactly. If you drink water containing, is anyone from Bengal, that area? Rich waters, and Nalgonda district, fluoride, right? Fluoride. So these used to be considered environmental pollutants, but people used to pay money to get rid of them. Today, people are paying money to get them. How situation has changed. And then when I told minister about this arsenic and cadmium and chromium, so minister immediately said, in my own district, I got arsenic. Please do something. Then I said, you give us money. And then he gave us $5 million to support this Australia-India joint venture. So what you have to do is, if you want to win your argument, again, this is because you are all young, upcoming, scientific leaders of the country. Don't hate politicians. They are from within our own societies, right? Who stops you becoming a politician? Doesn't even stop. It's only your choice that you made. Okay, I want monthly salary, comfortable life. We have chosen to be here. So what I'm saying is, if you pitch in the right sense, they will appreciate. And immediately we got the government's approval. Now we are trying to build this to a $50 million kind of partnership between Australia and India. Again, motivated by this fact. We need more professionals. We need girls. Gender parity is huge. You remember last time when we did our symposium in January, right? January, hardly any women participation. At least in India, the good thing is we have got more women and girls into STEM areas. I think our STEM participation is about 30%. But we need to still, jack it up. Anyway, so did you see what I'm meaning? As you go outer, the dependency of particular metal association with the mainstream metal becomes lesser and lesser. But by and large, I call them as exotic minerals or metals. Again, I'm using metals and minerals quite interchangeably. So, likewise, Mercury used to be. No, that's also a of interest. Critical mineral. Is that clear to everyone? Yeah. Okay. This is from one of our papers. I think we published back in 2017 in Ore Geology Reviews. So a little again, this is not of so much importance to you, except my good friend from geology or geophysics. So going back to here, lead, the mineral, the ore mineral, there are a couple of subtle differences between rock, ore, mineral. You are from different areas, different fields. If I go just by my slides, I don't know how much of that you will grasp. I'm going a bit of old school so that you really get because I want to make sure that you get a good understanding of critical minerals rather than just brush up. There's something called, don't we have different color pens? Can we ask, can we try to get for tomorrow? There's something called rock, R-O-C-K, rock stars, rock, mineral, ore. Rock can be just a random rock. And again, in one of the lectures, I'll cover something little detailed about how a rock becomes important. Rock may or may not contain valuables. It will surely contain, but again, there's something called crustal concentration. There's crustal abundance. Two things. Any rock that you take can literally extract gold, silver, any metal that we talk about here in a theoretical sense. कहीं से पत्थर निकालो, you can extract them. But the problem is the concentration. it will only qualify to be an ore when the concentration of that particular metal of interest, gold, when it reaches that 5 grams per ton. Before that 5 grams per ton, it may not qualify to be an ore. It can be just a rock. So there's something called crustal abundance. We talked about crustal abundance, crustal concentration. And when it has sufficient concentration to be economically extracted, because you remember when you dig up 1 ton, you only get 5 tons, 5 grams. So your mining has to pay for that, and then processing, and then transportation, and then refining, everything. The metal has to pay for everything, right? You have to move huge ground, and even before touching your ore body, you have to remove a lot of waste material, waste rock. So all of that cost it has to pay off, and then you have to still make profit. So today, what is the gold price? About $2,500 right? An ounce. Per tula, right? Yeah, very expensive. Now it's going. Yeah. Oh, that's right. That's right. Yeah, in the tailings, right? Yeah. Was it? Okay. Okay. Is it the duck and gold? No. So why gold prices are going up? Again, this is something a bit of digress, but a very important discussion. What does it indicate? No, no, no. I'm not talking of technology. I'm talking of something again. The sentiment. Why? What does commodity prices, especially gold going up, means to the world? Yeah, that's one good thing. No. See, when did, yeah, excellent. Yeah, that's one, too. But what is the fundamental reason, the underpinning reason? And it happened very rapidly soon after Trump took over. Do you remember? No, no, that's fine. I know. I am not debating on that. You are perfectly right. But why? Why people rush towards gold? Yeah, yeah. Recession is somewhat related. So when people see a bit of uncertainty in the stock markets, the best bet for them is gold. So you don't know whether if you invest in Adani or Ambani, whether you get or not. But better hold on to gold. You know which is the country which has maximum gold in the country? India. 40% of world's gold in every year comes to India. Thanks to our women, right? Cultural. In fact, when I was spending my sabbatical at Yale, so the guy Nadal, who was a PhD, then now he has become the chief of critical minerals mission at US in the US government, USGS. He showed a picture, when it came gold, Indian women with full gold. And I see a lot of Indian male also nowadays. I saw one guy who was, no offense to anyone. Yeah, that's right. So I think according to official statistics, India, like again, not much of that gold is held by government. Government only holds about 8 tons of gold in the Reserve Bank. But if you look at the overall gold, I think the US holds about 20 tons, the US government. And then people don't hold so much in the US or other parts. In India, people hold more than the government. And the combined total gold ownership in India would be around 30 tons. 30,000 tons. Not 8,000 tons is what the government holds in India. 30,000 tons would be total gold. And I think there is one temple in Kerala, Padmanabha Swami temple. It holds a lot of gold. So, for example, that's why India is very secure in a sense, and it's also used as a metric to control inflation. And when countries go bust, for example, US has a $37 trillion debt. That means where do you borrow? You're just printing money. That again leads to a lot of what you call inflation. Right? So that's one important thing measure. Like when gold prices go means that means there's a lot of uh, instability. That's a prime mover. Yeah, is this clear? Yeah, shall we go ahead? So these are the types of ores. Generally, ore is when you find a particular metal concentration sufficiently high enough to be economically mined, processed, smelted, refined. That's ore. O-R-E. Otherwise, it's mineral, it's rock. So, in a theoretical sense, every piece of rock that you find on Earth, you can extract a metal. But the enrichment factor is the key thing. If it is 1%, you can extract in copper. If it is any less than, say, the crustal abundance, there's something called crustal concentration. There's some 0.002% of copper will be present all over the world. Every grain of rock that you lift, you will find it. But what happens is the energy that you have to spend, the crushing, the grinding, the chemicals, all of that will make it inexpensive. So again, we'll touch upon that. So, but for now, let's park it that way. These are called ores. What are the types of ores that you find? Porphyry epithermal. Again, this is more geology, so our good friend knows them. Granite related. Third one is iron oxide copper gold, IOCG we call it, which again is the main thing for, if you look at the previous slide, most of the rare earths, can you see that? So rare earth family is associated with that. And then sub-aqueous volcanic related, orogenic, basin hosted. So generally now people are betting this also for rare earth elements. Alkaline intrusion related, superficial placer deposits, and then Permian and tertiary coals of Mesozoic, Jurassic Park, right? So these are the types of deposit types. These are the deposit types. Again, I'm not going to go. This is in the case of Australia, but again, similar analogy can be drawn for India also. And these are the major elements. The previous slide. So these are the major elements of that ore. And these are the potential companions. Companions are what? These. Yeah. Right. And then available in Australia. Again, you can map a similar thing for India also. You can create a similar map for India also. Right? Hmm? Okay. Now, it is useful to consider minerals in certain groups can be functional based on the functions that they fulfill. What are the functions the critical minerals fulfill? For example, here you got batteries. Yeah, batteries are very important. One of the key problem with key issue rather than problem. See why coal still remains the base load power. Coal power still remains the base load power because coal you can continue 24-hour operation and then you can produce energy. When do you think the energy demand will be peaking in a day? What time of the day? So you got 0 hour, right? 1 o'clock, 2 o'clock in the morning, 3, 4, blah blah blah, and then you got again 12 a.m. That's how your 24-hour cycle goes on, right? What time of the day you think your energy demand would peak? Morning, what time? So maybe let's say 6 to 10 ish. Is that right? 11 to 4 is it really? Less, probably. Oh, great, okay. Then the second peak would be what time? Maybe 6, let's say 6 to 10. 6 to 10. So this is when you have got huge demand. Now, you have no sun until say 7 o'clock, good sun, 7 o'clock in the morning, and no sun after say 6 o'clock or even 5 o'clock, I would say. So that means when your evening peaks up, you have no sun. That means you simply cannot have a solar panel and then produce energy. Are you seeing what I'm saying? So that is where batteries are so important. Why batteries are important? Why people are looking for batteries? For this storage. So you can only produce solar energy when sun is around, dawn to dusk, they say, right? When sun rises, then you can start producing solar. And same with wind. You can only produce wind when there's wind around. And once the wind stops blowing, you cannot produce. So hence, you need to have a backup. When you produce, and that's why, whereas coal power plant, you can run 24 hours. 24 hours. So that's still your base load. But now people are still producing in India because the energy demand is still growing because ours is still developing country. So a house that had 2 bulbs, now it has five bulbs. And a house that had 100 bulbs has 200 bulbs. So our energy consumption is going up for sure, household energy consumption. But what you can do is when you have solar, you can produce that time. That time you can lower your what you call coal-based energy bit, and then compensate. But in the long term, the storage is the only solution. Yeah? So if you look at that's why batteries are becoming so important. Lithium-ion batteries. So you require lithium, nickel, cobalt. Again, there are different configurations within that. So in some configurations, you do away with these three: nickel, cobalt, and manganese. Then LFP, we call it lithium. LFP. Does someone know LFP? Lithium. You said something. Okay. Lithium. It's lithium iron phosphate. Yeah. LFPs. Because there you don't require nickel, cobalt, and manganese. When you don't need, that means you can bring the cost down. That means you can easily afford it. And then even now people are talking of zinc ion, sodium ion batteries. But one of the main problems with other configurations is the storage density. So, for example, if you buy a Tesla car or if you have an electric car, again, say for example, I am from Mantani, which is about 220 kilometers from here. If you have to travel that distance, a Tesla car is easy. You can go and come back without charging. But if you have to travel from Melbourne to Sydney, which is about 1,000 kilometers, at least I have to charge it twice. Then the energy density is the key thing. Once you charge, how long you can drive. The problem with other battery configurations is the energy density. Yeah. So that's the batteries. And then vanadium flow batteries are also kind of being thought about. And then you got where you require rare earths for electric vehicles and wind turbines, and magnesium for different alloys. Yeah, magnesium alloys. And as far as electrification is concerned, you require solar photovoltaic inputs, which requires high purity silica, yeah, for wafers manufacturing, and then copper, indium, gallium, selenium, cadmium, and tellurium. And electrolyzers are required for various applications, including your hydrogen fuel cells and stuff like that, right? So platinum group of elements and titanium catalysts are important, and electromagnets and permanent magnets. So we talked about in the morning NdPr based magnets and Fe, boron, and other rare earth magnets, and then semiconductors. So these are kind of, again, you can go on and on for different applications. They are only for just uh, what you call commercial applications. Then you got strategic applications, defense, surveillance, satellite communications. They require a bunch of similar metals. Again, this morning we said 80% of US defense supplies China. So you see the vulnerability there, right? The geopolitics. So countries like Australia, for example, they have wanted to have 98 gigawatt photovoltaics by 2030. That means now they are commissioning about 135 projects, and same with 49 gigawatts of onshore and zero point 0.5 gigawatts of offshore kind of wind. So it's a massive scale of that are going to be needed. Yeah. Any doubts? Australia. Again, look at this. This is again one of my favorite. Uh, in 1980, if you look at how many of you were born before 1980s? None. Right? About 11 elements made up a typical printed circuit board. You know printed circuit board, right? PCBs. Your mobile phones have them, your laptops have them, everything. Typical PCB consisted of about 11 elements. By 1990s, you added 4 more to that count. Today, it's a pack of 45 plus metals or minerals. A mobile phone is nothing but 45 metals or minerals. Right? Why? Why do you think this happened? What was the key driver?
Innovation.
Yeah, why that innovation?
To reduce the size of the component.
Excellent. You said something else. One small thing.
To reduce the size.
Touch sensitivity. Excellent.
Reduce the size of the, reduce the power.
Power consumption. Brilliant. Super capacitors. Yeah, excellent.